computer is a device that has four primary functions: input, output, processing, and storage. It accepts data as input, processes it, outputs the processed data, and optionally stores it. All of this can be done on large quantities of data and at mind-boggling speeds. However, a computer in and of itself is actually quite dumb. It cannot solve problems on its own. It needs to be told how to solve problems. The computer programmer is the problem solver. It is this person who finds a generic set of steps to follow to come to a solution to a particular type of problem. A collection of such steps can be referred to as an algorithm. The steps of an algorithm are written as instructions that the computer can read that tell it how to process the input data to compute the appropriate output data. A computer is an electronic device, therefore it knows nothing about spoken languages. It knows only how to read electricity. That means we must translate our instructions from human understandable form into a form the computer can understand. Electricity flows through integrated circuits, which are made up of billions of tiny transistors. At the risk of oversimplifying the electrical engineering aspect, but in the interest of keeping this explanation as simple as possible, we will just say that they can be switched on or off. These two states, on and off, can be represented in the binary number system as 0 and 1. Humans typically think in terms of the decimal number system, meaning we have 10 numbers. When we reach the highest possible number and need to increment it further, we simply add another digit to the number, starting the sequence over, where 9 becomes 0 and we add a 1 to the left of it to get 10. It is believed by many that we came to use this numbering system as a result of having 10 fingers to count on. You can think of your computer as having only 2 fingers to count on. Therefore, all instructions for it must be given in binary. If you're still having trouble grasping the concept, you can also think of it as if your computer only understands Morse code, which has just 2 characters in its alphabet. Since data is read and processed in binary, we refer to each binary digit as a bit. There are 8 bits in a byte. A byte is the smallest unit of data that can be addressed. Because translating every possible instruction into a series of zeros and ones can be both tedious and error-prone, we have developed what we refer to as low-level programming language known as assembly. Assembly uses a mnemonic to represent each low-level machine instruction or operation. It is converted into machine code by a program known as an assembler. Because even assembly itself is also very tedious and error-prone, we've further gone on to develop high-level programming languages. These are languages that are more easily read and used by humans, but which also have very specific syntax rules that are used to convert the human-readable code into machine-readable code. As previously mentioned, C++ is a high-level programming language. The program used to do this conversion is known as a compiler. When you finish writing code for a program, you need to build that code into executable machine code. The build process involves 3 steps: the preprocessor, the compiler, and the linker. We'll get more into what these do once we start coding. There are many different categorizations of software, but most fall under 2 general categories: system software and application software. Your operating system is system software, as it is the base program your computer runs to interface with its hardware and allow other software to run. Application software is pretty much everything else you run on your computer, such as web browsers, games, and word processors. Games are application software, so we won't focus much on system software. Before we move on, I'd like to quickly introduce you to some common terminology that you should be familiar with, as these terms may be used over and over throughout these lessons. Some have already been introduced, and some are new, but be sure to learn them all. ASCII, American Standard Code for Information Interchange. This is used to represent characters. ASCII characters are represented in 1 byte, therefore there are 256 different possible ASCII values. Unicode. Like ASCII, Unicode is used to represent characters. However, Unicode characters are represented in 2 bytes, allowing for a wider variety of international languages. Decimal system, base 10 number system, the one we normally use in day-to-day speech. Binary system, base 2 number system. There are only 2 numbers in this system, 0 and 1. Hexadecimal system, base 16 number system. There are 16 numbers in this system. 0 through 9 is represented by 0 through 9, and 10 through 15 is represented by A through F. Octal system, base 8 number system. There are 8 numbers in this system. Kilobyte, 1000 bytes or 1024 bytes. 1024 is a power of 2, and 1000 is a power of 10. Machines think in binary, so their hardware storage often comes in powers of 2. Humans usually think in decimal, so sometimes amounts of memory are given in decimal. Both are frequently used by advertisers, which can cause confusion for consumers. A 1 gig disk drive might actually be 10 to the 9th bytes, instead of 2 to the 30th, so you'd be getting less storage. Furthermore, some of the space gets used for formatting. This is why you might buy a 300 gig hard drive, but only see maybe 280 available when you boot up. An uppercase K is supposed to be used for base 2, and a lowercase k is supposed to be used for base 10, but this is not a standard and not everyone abides by it. Kilobit, 1000 bits or 1024 bits. Once again, kilo here is used to represent both base 10 and base 2 measurements, so it can be confusing. Bits are often used to advertise throughput speeds by internet service providers to give the illusion of a higher number than using kilobytes per second. Floating point number, a fraction, also sometimes referred to as a real. CPU, Central Processing Unit, the hardware that processes data on your computer, often referred to as the brains of the computer. Compiling, translating human-readable code into machine-readable instructions. Assembly, a low-level programming language. Each statement corresponds to a single machine code instruction. It is converted into executable machine code by an assembler. When you compile C++, your code actually gets translated into assembly first, then assembled into relocatable object code. GUI, Graphical User Interface. Pretty graphics used to facilitate input and output for the user of the software, for example using menus and buttons instead of command lines. Millisecond, 1/1000th of a second, abbreviated as ms. The amount of time it takes for a program to execute an operation is often measured in milliseconds. Algorithm, a set of steps that describe how to solve a certain kind of problem. Bug, a problem in your code that causes crashes, hangs, or otherwise unintended behavior. Compiler error, an error in the syntax of your code. Linker error, your code is syntactically correct, but your linker can't find all the pieces it needs. Crash, your program compiles and links, but when you run it, it stops working and has to be shut down. Hang, your program gets stuck but doesn't necessarily crash. Debug, to find and fix errors in your program. Armed with some basic terminology and a desire to create, let us move on to setting up our environment for programming. For the remainder of this lesson, I will walk you through setting up an IDE. IDE stands for Integrated Development Environment. When you write code, you need something to write it on. This is typically done in a plain text editor, and the code you write is referred to as source code. Notepad could work fine. Once that code is written, you run it through a compiler which invokes the preprocessor before compiling. Then it attempts to translate the code into machine code. If the compiler comes across syntax it does not understand, it will generate an error message and will not compile. You must fix the error before it can be compiled. Once your code is compilable, the compiler will translate it into machine code and produce one or more output files known as object files. Then the linker is invoked. The linker brings it all together to produce an executable file. On Windows, this would be the .exe that you double-click to run a program. These are a lot of steps. Though you can do them each separately in a command line interface, it's much easier and wiser to do them in an IDE. The IDE is a software package that bundles the compiler, linker, and text editor together all in one. You write code into the text editor, press a button to invoke the compiler, and then an executable is spit out into your project folder. There are many IDEs available. A common older one is Dev C++, but this is no longer maintained and no longer complies with the current C++ standard. Don't use it. There is also CodeBlocks, which is a free IDE available for all platforms. There are many others, but one that dominates the industry is Microsoft's Visual Studio. As a Linux fanboy and advocate of cross-platform software, I typically loathe Microsoft products and business tactics. However, Visual Studio is a godsend. It comes with a wonderful set of indispensable features. Although it has several of Microsoft's own extensions that are not a part of the C++ standard, standard C++ code will compile on it. As of this video, most modern compilers do not yet fully support C++ 11, and VC++ is no exception. It does support many of C++ 11's new features, but some are still missing. Because this is such a widely used and insanely awesome IDE.
2013. If you are unfamiliar with IEEE acronyms, you'll be pleased to know that SWEBOK stands for the Software Engineering Body of Knowledge. It's a fundamental document in the field of software engineering. It was released during the month that I was giving this talk, and that version is an update of a 2004 edition, one done almost a decade ago. Now, when I talk about SWEBOK within the IEEE, I get an interesting set of reactions. I'm told by some that you simply cannot engineer software, that it's impossible. Others have told me quite blatantly that it is possible to engineer software, but we just don't. Another group, quite substantial, has told me that indeed it is possible to engineer software, and we don't, and what we need to do is follow the example of electrical engineering more closely. Finally, there have been a few who say that software engineering is actually just another form of electrical engineering, and electrical engineering is merely a form of physics. In fact, not one of these assertions is true. Software engineering is completely unrelated to electrical engineering. It also, as it turns out, has very little relation to hardware, as contradictory as that may seem. It certainly has no connection at all with physics. Its origin comes from a very different source. And that source begs the question about software engineering: what is being engineered? To what entity or artifact are we applying engineering principles? We will start our story in 1946 with the creation of the ENIAC computer in Philadelphia, even though our story actually has much earlier origins. And we'll begin it with that classic picture, guy holding up stuff, an engineer displaying a piece of hardware in order to illustrate a more abstract concept. We all know the classic picture of Steve Jobs on the right holding up the first iPhone, but it models a picture of two people, Herman Goldstine and John von Neumann, holding up a piece of the ENIAC to illustrate the power of the computer. Goldstine, who was von Neumann's assistant, really helped to invent software. He grasped that the problem of commanding these machines to produce numbers was hard and that it required discipline. He drew his ideas heavily from the field of manufacturing engineering. Indeed, the word program came from production engineering. You programmed a factory. You produced a program of production. In developing his ideas about programming, he borrowed the idea of the flowchart from production engineering. These charts were originally designed to trace how goods moved through a large factory. Goldstine applied them to software. Now, of course, Goldstine was not the first person to think about software, and those who preceded him did it with mechanical devices. Howard Aiken and Konrad Zuse, of course, were developing some of the same ideas at about the same time, but they were using mechanical computers. Aiken had the Mark I at Harvard, which is pictured here, and Konrad Zuse was building the Z1 in Germany. And if you really want to look at mechanical origins, you can go back to the 19th century and the analytical engine of Charles Babbage. In developing his ideas on software, Herman Goldstine was really following a golden age of production engineering that began in the 19-teens and the 1920s. The engineers of that era believed that the world was entirely knowable, that if you got enough detail about any problem, you could solve that problem. Those ideas we have come to know as rational positivism. If you look at the influential thinkers of the time, you see them driving this idea forward until a few of them began to grasp that there is going to be something more needed in order to solve production engineering problems. These thinkers include Henry Ford, Frederick Winslow Taylor, Henry Gantt, the Gilbreths, of course, and Walter Shewhart. Ford, of course, is the giant of the age. He understood the need of analyzing, of breaking apart steps of production and ordering or sequencing those steps. He explained the need of simplifying manufacturing processes, of having a unified product, and finally of controlling the information flow in production. Henry Gantt looked at the problem of sequencing as well, and developed graphical techniques for analyzing the process and for producing a clear representation of ordered steps. Frederick Winslow Taylor was perhaps the most influential thinker of this era. He promoted the idea of analyzing any piece of work and use that information to optimize the entire production process. His book, The Principles of Scientific Management, is one of the most influential texts of the 20th century, and certainly has had tremendous impact upon software engineering. He took as his slogan the one right way, and argued that every production process had one way that produced the best results. Frank and Lillian Gilbreth were a husband and wife team who were followers of Frederick Winslow Taylor, but ultimately their work illustrated some of the limitations of Taylor's methods. They studied motion and tried to make the movement of people more efficient. To describe human motion, they came up with a concept of the third leg, it's their name in reverse, that were basic descriptions of how you could move your hands, feet, and other parts of your body to do work. They saw this as a tool for describing production. But with this language, or means of describing production, they found some basic problems. It was not a unique language, nor was it complete. Certain motions could be described many ways, and some could not be described at all. In fact, other individuals and engineers had begun to see some of the limitations of Winslow's techniques already. Samuel Insull, for example, recognized that there were engineered systems which were too complicated and involved too many people to know perfectly, and that you had to work with limits on perfect knowledge. In his work, which involved looking at electrical distribution, transmission, and generation networks, he saw patterns in aggregation and began to develop techniques for managing those systems based on collective experience. He knew he did not know it all, but he also knew that he could engineer it to minimize the effect of his ignorance. More than Insull, and more than the Gilbreths, Walter Shewhart showed the limitations of Taylor's work and laid the foundation for modern software engineering. Shewhart was a production engineer at the old American Telephone and Telegraph, and he was charged with implementing the company's goal of universal service. In particular, he was responsible for making sure that the phone equipment, phone sets, phone switches were all made the same way, had the same quality, and could be used anywhere in the system. In building his ideas, he was inspired by the physics of his age, the 1930s, with its emphasis on probability and the fact that no state of matter, certainly at the quantum level, was ever knowable. He observed that in fact the human world was unknowable, and that one had to put in place a system to manage ignorance. His system used a cycle of steps that have come to be known as the cycle of continual improvement. The idea was that you started by designing a product, then you built the product, and then you deployed and tested the product. And once you had gone through those steps, you would start the cycle again, redesigning it, rebuilding it, and redeploying it. For software, several decades later, this process becomes the software life cycle, in which software is viewed as a system that is always being revised. You start by defining the requirements of your software, and then you design the software system, you code it, you debug it, and then you install and configure it in the production system. Next, you operate the system, and then you gather information from the operations that tell you how you can assess what you have done, and then you start the cycle over one more time to start with requirements for changes, design, and code. This cycle never stops, but it gives you a way of managing change, of managing the complexity of the system, and for guiding it towards a target that is ultimately unreachable. Shewhart's ideas became part of software development following an event in the 1960s that we've generally called the software crisis, though it's not clear how much of a crisis it actually was. There was at the time a perception that there were insufficient trained personnel to develop software. It was a time when software was still very much a local activity, something that you produced for your business but would never share with another business. In 1964, IBM had come out with the 360 series of computers, which rapidly became the largest installed base of computers. This increased the demand for programmers, and it also created a large market for unified software packages. In the midst of this crisis, A group of software professionals met at a conference in Garmisch, Germany, that was sponsored by NATO, the North Atlantic Treaty Organization. This conference was called to consider the issues of software engineering, in particular to produce high-quality software products that could be used on many machines at different sites. This conference also coincided with an important announcement by IBM, which initiated the software products industry. In 1968, IBM announced that it would no longer be giving away free software, a move that's generally called the unbundling decision. At the Garmisch conference, we can identify at least 3 competing visions to shape the new field of software engineering. The first came from Edsger Dijkstra, a Dutch computer scientist, who was known for structured programming. He wanted to see people pay attention to how you organized the code, how you worked with the artifact, and how you could use formal methods to prove the correctness of your system. A second vision came from Doug McElroy. He was interested in a process of software engineering that resembled mechanical engineering, that would have standard parts, standard components, he called it, that could be assembled into final systems. The third vision came from Peter Nauer, and his vision closely coincided with that of Walter Shewhart. He noted that many of the problems encountered in software engineering resembled that of management, and ultimately his line of thought led to the adoption of the software lifecycle and the methods of Walter Shewhart. Following the Garmisch conference, we see an interesting part of the work of developing software engineering shifting to the IEEE Computer Society. The society was new. It was formally organized in 1970, even though it had roots that can be easily traced to 1946 and arguably placed in 1938. The society developed the ideas of software engineering primarily as a series of standards. Standards that described how the engineer should operate, the kind of work that should be done, and how we thought about the problem of software engineering. The first of these standards, 829, on test documentation, appeared in 1983. The next, 830, on requirement specification, appeared the following year. 1002, the taxonomy for software standards, appeared in 1987, and a year later, Standard 730 on quality assurance plans made it clear that when you talked about software engineering, you were talking about quality control and you were utilizing the ideas of Shewhart. In 982, the standard released that same year, we defined what kind of measures you would use to define dependable software. Configuration management was a standard that appeared 2 years later in Standard 828. And finally, the software lifecycle is systematized in 1991 and released as Standard 1074. All of these standards, taken together, led directly to the formation of SWEBOC. SWEBOC began its life in 1993 as the product of the Software Engineering Coordinating Committee. This committee was looking at a number of aspects of software engineering. Their first major product appeared in 1995 was an ISO standard, International Standards Organization, on the software lifecycle. This document fully incorporated all the ideas of Walter Shewhart as the basis of software engineering. It's numbered 12027. SWEBOC appeared almost a decade later, in 2004. This original version has been used for nearly a decade. It, too, has become a standard of the International Standards Organization. It carries the number 19759. It is a standard. It describes how people need to operate, how they need to think, and how they need to work as software engineers, and what it means to engineer properly a piece of software. The new 2013 revision of SWEBOC has updated that original one, now in use for almost a decade, to the current practice. It has now been improved with an honest 25 years of experience in developing software methods, and it incorporates the new software engineering techniques of lean development and agile development. It shows very clearly that software engineering is in fact a multidisciplinary topic. And it also asks the question, what indeed are we engineering when we engineer software? The search for an answer to that question takes us back to the Shewhart cycle. We certainly are engineering an artifact, software, though that artifact is never really seen by the user. We are also engineering a system in which the actions of software are usually seen in other machines, or in people, or in work. We certainly are engineering human actions, as almost all software involves some interaction with people or organizations. And finally, we are engineering the role of the engineer, because software is never done, and the only properly engineered software is that in which a skilled professional takes responsibility for its life cycle. This is David Alan Grier.